Have you ever just stopped and wondered how we did it? How humanity went from just looking up at the stars to writing down the actual mathematical rules that run the entire universe? Well, let's dive into that incredible story.
It all boils down to a really simple, fundamental question. Why isn't everything just random chaos? Why does it feel like there's an underlying logic, a set of rules that the universe plays by, day in and day out? That question, right there, is the seed for basically all of science.
So the very first clue we ever got was noticing something that's so simple it's profound. Nature has patterns. It does the same things over and over again. This wasn't some complex discovery in a lab. It was just about paying attention.
And this is the absolute bedrock of it all. If you put things in a similar situation, you're going to get a similar result. You drop a rock, it falls. You do it again under the same conditions, and guess what? It falls the exact same way. It's that consistency that lets us even begin to predict what's going to happen next. Okay, so what starts as a simple observation, well, it hardens into a core belief. Right? We slowly shift from thinking, well, it happened that way last time, to it will happen that way next time because there's a reason. This idea of causality, that things don't just happen, they are caused, that's the engine that drives the whole search.
But this leads to a huge problem, a real roadblock for early thinkers. Okay, fine. We can predict what happens in a situation we've already seen, but what about all the ones we haven't seen? I mean, the number of possible scenarios is literally infinite.
Yeah, think about it like this. You totally understand how a ball falls in a still room. Simple. But what happens if you add a new twist, like a powerful fan blowing air up from underneath? All of a sudden, your simple rule, things fall, doesn't quite cut it. Does that mean we need a totally new rule for every single variation we can think of? And that, right there, is the question that stopped progress for centuries. If you have to see and test every single one of the infinite possibilities to know what happens, well then real prediction is impossible. We'd just be stuck making a giant list of facts forever. There had to be a smarter way.
The big breakthrough, the game changer, was a total shift in thinking. Instead of getting bogged down in every complex event, people started asking, wait a minute, what if all this complexity is just simple stuff, all mixed together? What if we could find the simpler rules hiding underneath?
This powerful idea has a name, reductionism. And it's probably the most important tool in the entire scientific toolkit. It's the core belief that you can understand that chaotic ball and fan situation not by creating a new ball-fan law, but by understanding the law of gravity, plus the laws of air pressure, and just seeing how they interact. And this gives us a kind of recipe for discovery. First, you observe a consistent pattern. Second, and this is the absolute genius part, you abstract. You stop thinking about this specific ball or that specific planet, and you start thinking about the general properties they share, like mass or force. Third, you translate that relationship into math. And finally, you try your absolute best to prove it wrong. You test it and test it and test it again. And by following this exact process, we made the incredible leap from just noticing things to writing down powerful predictive physical laws. This is where it all comes together. Let's take momentum as a perfect example of that abstraction step. It's not just about how fast something's going. It's a deeper concept. It's quantity of motion, right? It combines an object's mass and its velocity into one single fundamental idea. It's a much more useful way to describe what's really going on. Now, this is where it gets really, really cool. This equation is Newton's second law, but it's the real version, the more fundamental one. Most of us learned F equals ma in school, right? Well, that's kind of the simplified version. It only works when an object's mass is constant. The deeper truth is right here. Force equals the rate of change of momentum. And that's huge because it works for everything, even for a rocket that's burning fuel and getting lighter as it goes. What a force really does is it changes momentum. This one beautiful, elegant equation is the ultimate result of that whole journey.
And this is the incredible payoff. Remember our problem of infinite scenarios? Well, by finding that one deep rule, we can suddenly go back and solve them. A falling apple and a planet in orbit are no longer two different problems. They're just two different applications of the exact same underlying law. That is some serious predictive power. Okay, so we've found these unbelievable laws. But that brings us to an even deeper, more philosophical question. What exactly is a scientific law? Is it some absolute truth that the universe must obey? Or is it something else? For a long, long time, people thought of these laws as commands. But the modern scientific view kind of flips that on its head. A law isn't a command, it's a description. It's a human-made model that does a really good job of summarizing how nature has always been seen to behave. The law doesn't tell nature what to do. Nature's behavior tells us if our law is any good.
And this is so important to get. No matter how many experiments you run, you can never prove a law is 100% true for all time and all places. But every single time it passes a test, our confidence in it grows. Science isn't about finding final, absolute proof. It's about building the most reliable, battle-tested models of reality that we can.
And you see this play out perfectly in the history of physics. Newton's laws, an unbelievably good model for the world we experience every day. But when you push to extremes, like things moving near the speed of light or down to the scale of single atoms, we find we need a better model. Relativity and quantum mechanics don't prove Newton was wrong. They just show that his model had limits. They're the next, more refined chapters in our amazing book of descriptions.
So, we end up right back where we started, but with a whole new perspective. Our laws aren't divine commands. They're our best, most powerful summaries of a universe that is amazingly consistent. There are models, and we are constantly testing them, refining them, and pushing them to their limits. And that just leaves one incredible question. What will they help us see next?